So let's talk about freezing point changes before we talk about boiling point changes. And the reason we talk about freezing point changes and boiling point changes separately is that it would end up being kind of a long video. But here's the thing. We're going to limit ourselves to solids dissolved in liquid solvents. So something like sodium chloride dissolved in water, sugar dissolved in ethanol, something like that. And the reason we're going to do that is that it makes the explanation a bit simpler and the formula is a lot easier to work with. Now we're also going to assume that whatever we're dissolving in our solvent is fairly dilute, so not super high concentration. So when we talk about these, we're talking about molarities and molalities less than 1.1 molar. So what happens to the freezing point of a material when you add a solute to a solvent? Well, what ends up happening is you have what's called freezing point depression. So the freezing point of water is 0 degrees C. If we add salt to it, the freezing point becomes less than 0. So conceptually, what's going on? Why does this happen? Well, to explain that, we have to explain what happens when a material freezes. So if we look at water, when water freezes, it goes from H2O molecules flowing past each other to a well-organized crystal. So particularly with water, we get a hexagonal crystal. That's going to look something like this, with a whole bunch of repeating units. So water is a very organized material. In fact, most solids are when they freeze. Now, if this is just water, let's say we throw in something like sodium chloride, Na and Cl. Well, these NAs and these Cls have to go somewhere, and if you look at this crystal, there's really nowhere for them to go. So you've got a Cl minus, it's preferably going to go between two hydrogens, but we're always going to have positive and negatives lining up. So now you have to accommodate a negative and a positive. The same thing's going to be true with the sodium. You have to accommodate with the sodium, so you're going to have to find two things to stick next to that are both negative. Effectively, what we do is we disrupt a crystal's structure when we add a solute into it. So this is why we see the freezing point go down. Now, what this depression is representing is that there are two ways the crystal can accommodate the solute in its final structure. One is that it can count them as defects in the crystal structure. Well, the defects are higher in energy, so we have to go to lower temperatures to make them thermodynamically favorable. So that's one interpretation, and that's what some materials do. When they freeze, you find the solute within the material, within the crystal itself. The second option, which also occurs, is that it will actually begin to separate out the solute. So let's say hypothetically water would do that. Well, as we begin to freeze it, we're going to form perfect ice crystals, but the water that hasn't frozen yet is going to get increasingly concentrated with sodium chloride and sodium chloride until finally the water is completely removed from the sodium chloride. So the second interpretation, depending on what the material does, if it does separate out the solute, that lower temperature is reflecting the fact that we are having to separate out the solute, and that temperature difference is reflecting the work we had to do to get it out. Now, that is a qualitative interpretation. Delta T, freezing point depression, is always negative. We will always decrease in temperature if we add a solid solute to a liquid solvent. But we can quantify this as well, and we have a very simple relationship for this. Delta T equals Kf times I times little f, molality. So, our freezing point change, our delta T, how far we move away from the freezing point, and this number is always going to be positive, although we decrease the number, is proportional to Kf. Now this is solvent specific. So the Kf for water does not change based off what you're dissolving in. The Kf for acetone, the Kf for ethanol, they're all the same. And the reason why they're the same is this sufficiently dilute stipulation. If we don't have high concentrations of our solute, we don't have to worry about it. We can just say it's the same regardless of what's being dissolved. The M here is your molality. And that's where this unit of measurement begins to pop up and trying to explain basically how many moles you have per kilogram of solvent. Reason why we're going to work with this and not molarity is that that kilogram solvent reflects the fact that the solvent doesn't really care what's in there. So when you work with molarity, you have the liters, that's going to depend on the density of solution. This is just saying how many moles of this material are breaking up the solvent. Now we do need to work with moles because we need to know how many individual ions or molecules are disrupting the crystal structures. The other thing we need to know here is I. The I here is your Van 't Hoff factor. Now your Van 't Hoff factor describes how many different things your solute breaks into. So if we had something like sodium chloride, we start with 1 mole of sodium chloride and it breaks into 2 moles of one of sodium, one of Cl. So there's twice as many things to disrupt. Whereas if we had something like sucrose doesn't break apart in water, so the Van't Hoff factor for sucrose is sitting around 1. This formula right here basically quantifies how much we disrupt that crystal structure and the amount of heat we either have to remove to accommodate these crystal structure disruptions within a defect structure, or how much heat we have to remove to basically separate the solute. But this is your relationship for freezing point depression.